Here's a ballpark estimate for rewiring a house. Time estimation for rough-in work, assuming a single worker working 10-hour days, 5 days a week, is estimated at 2 to 3 weeks. Finished work, including wiring, outlets, switches, and fixtures, is estimated at 1 to 2 weeks. For materials estimation, you'll likely need between 5,000 and 7,000 feet of 12.2 and 14.2 non-metallic cable. Expect to install approximately 50 to 60 receptacles, 30 to 40 switches, and 100 to 150 junction boxes. The number of circuit breakers needed, based on the estimated number of branch circuits, is around 15 to 20. The service upgrade cost is already priced separately. Miscellaneous materials like straps and connectors are estimated to cost between $500 and $1,000. Cost estimation for materials is estimated to be $3,000 to $5,000. Labor costs are estimated to be between $6,000 and $9,000. Therefore, the total cost for the rewire is estimated to be between $9,000 and $14,000. Keep in mind that this is a ballpark estimate and actual cost may vary depending on several factors. Firstly, the complexity of the wiring layout can significantly impact the time and cost. Secondly, the accessibility of wiring areas plays a crucial role in determining the ease and speed of the project. Thirdly, the cost of materials can fluctuate depending on your location and the supplier you choose. Fourthly, labor rates vary depending on the electrician's experience and the prevailing market conditions. It's always a good idea to get multiple bids to compare costs and ensure you're getting a fair price for the work. Offering a warranty for your work can provide the homeowner with peace of mind and demonstrate your commitment to quality. Be sure to explain the scope of work and estimated costs to the homeowner clearly and thoroughly to avoid any misunderstandings down the line. When starting a rewiring project in a house, there are important steps and considerations to keep in mind to ensure safety, efficiency, and compliance with electrical codes. Firstly, before commencing any work, it's crucial to obtain the necessary permits from your local authority or building department. These permits ensure that the work meets the required safety standards and regulations. The electrical codes, such as the National Electrical Code, or NEC, provide guidelines for safe and proper electrical installations. Familiarize yourself with the latest edition of the NEC and any local amendments that may apply in your area. Secondly, a comprehensive assessment of the existing electrical system is essential. This involves inspecting the wiring, outlets, switches, and other components to identify any potential hazards, such as damaged or deteriorated wiring, overloaded circuits, or outdated devices. Pay close attention to areas where the wiring may be exposed or accessible, such as attics, basements, and crawl spaces. Document your findings and create a detailed plan for the rewiring project. Thirdly, safety should always be the top priority when working with electricity. Before starting any work, always disconnect the power supply to the circuit or area you'll be working on. Use appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools to minimize the risk of electric shock or injury. Work in a well-lit and ventilated area to ensure good visibility and prevent the buildup of hazardous fumes. Fourthly, when selecting wiring and other electrical components, it's important to choose materials that are appropriate for the intended application and comply with the electrical codes. Use non-metallic, or NM, cable for most residential wiring applications and ensure that the wire gauge is suitable for the circuit's amperage rating. Choose receptacle switches and other devices that are listed by a recognized testing laboratory such as Underwriters Laboratories or all to ensure they meet safety standards. Fifthly, proper wiring techniques are essential for ensuring a safe and reliable electrical system. When running wires, avoid sharp bends or kinks that could damage the insulation. Secure the wires to the building structure using staples or cable ties, and maintain proper spacing between wires to prevent overheating. Make sure all connections are tight and secure to minimize the risk of loose connections or arcing. Sixthly, grounding is a critical aspect of electrical safety. Ensure that all circuits are properly grounded to provide a path for fault current to flow back to the source, tripping the circuit breaker or fuse and preventing electric shock. Connect all metal enclosures, such as junction boxes and appliance housings, to the grounding system using grounding wires or grounding screws. Seventhly, when installing receptacles and switches, follow the manufacturer's instructions carefully. Ensure that the devices are securely mounted to the wall or box and that the wiring connections are properly made. Use wire connectors or terminal screws to make secure connections, and avoid using tape alone as it can loosen over time. Eighthly, proper labeling and identification of circuits is essential for troubleshooting and maintenance purposes. Label each circuit breaker or fuse in the electrical panel with a clear and concise description of the circuits it serves. Use a circuit tracer to identify the circuits and ensure that the labeling is accurate. Ninthly, after completing the rewiring work, thoroughly inspect the entire system to ensure that all connections are tight, all components are properly installed, and all safety requirements are met. Test each circuit to verify that it is functioning properly and that the voltage and amperage are within acceptable limits. Tenthly, schedule a final inspection with your local authority or building department to obtain approval for the rewiring work. The inspector will verify that the work meets all applicable codes and standards and issue a certificate of compliance. Remember that electrical work can be dangerous, and it's always best to consult with a qualified electrician if you're not comfortable performing the work yourself. By following these steps and considerations, you can ensure that your house rewiring project is completed safely, efficiently, and in compliance with electrical codes. Here are some additional points to keep in mind when estimating the cost and time for a house rewiring project. Firstly, consider the age and condition of the existing electrical system. Older homes may have outdated wiring, such as knob and tube wiring, which may need to be completely replaced. The presence of asbestos insulation can also add to the cost and complexity of the project. Secondly, assess the complexity of the wiring layout. Homes with multiple stories, complex floor plans, or numerous additions may require more time and materials to rewire. Accessibility of wiring areas such as attics, basements, and crawl spaces can also impact the project's duration and cost. Thirdly, determine the scope of the rewiring project. Will you be replacing all of the wiring, outlets, and switches, or just upgrading certain circuits? Will you be adding any new circuits or electrical devices, such as recessed lighting, ceiling fans, or dedicated circuits for appliances? Clearly define the scope of work to ensure that your estimate is accurate. Fourthly, factor in the cost of materials. Prices for wiring, outlets, switches, and other electrical components can vary depending on the brand, quality, and supplier. Obtain quotes from multiple suppliers to ensure that you're getting the best possible price. Fifthly, estimate the labor costs. Consider the hourly rate of the electrician, as well as the number of hours required to complete the project. Factor in any additional labor costs, such as helpers or subcontractors, if needed. Sixthly, include a contingency fund in your estimate to cover unexpected costs or delays. It's always a good idea to have a buffer of 10 to 15% of the total project cost to account for unforeseen issues. Seventhly, obtain multiple bids from qualified electricians. Comparing bids from different contractors can help you get a better understanding of the average cost for the project and ensure that you're getting a fair price. Eighthly, check the electrician's credentials and experience. Make sure the electrician is licensed, insured, and has experience with residential rewiring projects. Ask for references from previous clients and check online reviews to get a sense of their reputation and quality of work. Ninthly, review the electrician's contract carefully. Make sure the contract clearly outlines the scope of work, estimated costs, payment schedule, and warranty terms. Avoid signing a contract that doesn't provide sufficient detail or that contains ambiguous language. Tenthly, communicate openly with the electrician throughout the project. Keep the electrician informed of any changes or concerns you may have, and address any issues promptly to avoid delays or misunderstandings. Regular communication can help ensure that the project stays on track and that you're satisfied with the results. By considering these additional points, you can develop a more accurate and comprehensive estimate for your house rewiring project and ensure that the work is completed safely, efficiently, and to your satisfaction. In residential electrical systems, branch circuits are a fundamental aspect of distributing power throughout the house. They originate from the main electrical panel and extend to various outlets, lights, and appliances. Understanding the components and configurations of branch circuits is essential for safe and efficient electrical wiring. Firstly, a branch circuit consists of several key components. These components include the circuit breaker or fuse in the main electrical panel, which protects the circuit from overloads and short circuits. Wiring, typically non-metallic cable or NM cable, carries the electrical current from the panel to the outlets in devices. Outlets, switches, and light fixtures provide connection points for appliances and lighting. Junction boxes enclose wiring connections and provide a safe and accessible location for splices. Secondly, branch circuits are typically classified by their amperage rating. Common residential branch circuit ratings include 15 amps and 20 amps. A 15-amp circuit is typically used for lighting and general-purpose outlets, while a 20-amp circuit is used for appliances that draw more power, such as kitchen appliances and air conditioners. The amperage rating of a circuit determines the maximum amount of current it can safely carry. Thirdly, the National Electrical Code, or NEC, specifies the number of outlets and lighting fixtures that can be connected to a single branch circuit. The NEC provides guidelines to prevent overloading circuits, which can lead to overheating, fire hazards, and damage to electrical equipment. The number of outlets allowed on a circuit depends on the circuit's amperage rating and the type of load being served. Fourthly, branch circuits can be wired in different configurations, such as a series circuit, a parallel circuit, or a combination of both. In a series circuit, all of the devices are connected in a single path, so the current flows through each device in turn. If one device fails, the entire circuit will be interrupted. In a parallel circuit, each device is connected to the circuit independently, so the current flows through each device separately. If one device fails, the other devices will continue to function. Most residential branch circuits are wired in parallel to ensure that individual devices can be turned on or off without affecting the other devices on the circuit. Fifthly, grounding is a critical aspect of branch circuit wiring. Grounding provides a path for fault current to flow back to the source, tripping the circuit breaker or fuse and preventing electric shock. All outlets, switches, and light fixtures must be properly grounded to ensure safety. Grounding is typically achieved by connecting the metal enclosures of electrical equipment to the grounding system using grounding wires or grounding screws. Sixthly, arc fault circuit interrupters, or FSIs, are devices that are designed to protect against electrical fires caused by arc faults. Arc faults occur when there is an unintended electrical discharge between two conductors, which can generate heat and ignite nearby materials. FSIs detect arc faults and quickly interrupt the circuit to prevent a fire. The NEC requires FSIs to be installed in certain locations, such as bedrooms and living rooms, to provide enhanced protection against electrical fires. Seventhly, ground fault circuit interrupters, or GFCIs, are devices that are designed to protect against electric shock caused by ground faults. Ground faults occur when there is an unintended electrical path between a current-carrying conductor and ground, which can create a shock hazard. GFCIs detect ground faults and quickly interrupt the circuit to prevent electric shock. The NEC requires GFCIs to be installed in certain locations such as bathrooms, kitchens, and outdoor areas where there is a high risk of electric shock. Eighthly, when wiring branch circuits, it's important to use the proper wiring methods and techniques. All wiring must be installed in accordance with the NEC and any local amendments. Use non-metallic cable, or NM cable, for most residential wiring applications and ensure that the wire gauge is suitable for the circuit's amperage rating. Secure the wires to the building structure using staples or cable ties, and maintain proper spacing between wires to prevent overheating. Ninthly, proper labeling and identification of branch circuits is essential for troubleshooting and maintenance purposes. Label each circuit breaker or fuse in the electrical panel with a clear and concise description of the circuits it serves. Use a circuit tracer to identify the circuits and ensure that the labeling is accurate. This will make it easier to locate and identify circuits when performing maintenance or troubleshooting electrical problems. 10thly, regular inspection and maintenance of branch circuits is essential for ensuring their safety and reliability. Inspect the wiring, outlets, switches, and light fixtures for any signs of damage or deterioration. Test GFCIs and FCIs regularly to ensure that they are functioning properly. Replace any damaged or outdated components to prevent electrical hazards. By understanding the components, configurations, and safety requirements of branch circuits, you can ensure that your residential electrical system is safe, efficient, and compliant with electrical codes. Non-metallic, or NM cable, is a type of electrical wiring commonly used in residential buildings for branch circuits, appliance circuits, and other general wiring applications. It consists of 2 or more insulated conductors enclosed within a non-metallic sheath, providing protection against physical damage and environmental factors. Understanding the characteristics, applications, and installation requirements of non-metallic cable is essential for safe and reliable electrical wiring. Firstly, non-metallic cable, or NM cable, is available in various sizes and configurations to suit different applications. The most common sizes used in residential wiring are 14 gauge, 12 gauge, and 10 gauge. The gauge of the wire indicates its thickness, with smaller numbers indicating thicker wires. The appropriate wire gauge depends on the circuit's amperage rating and the type of load being served. NM cable typically contains 2 or 3 conductors, including a hot wire, a neutral wire, and a ground wire. Secondly, non-metallic cable, or NM cable, is suitable for use in dry locations where it is not exposed to moisture, chemicals, or physical damage. It is commonly used for wiring branch circuits, outlets, switches, and light fixtures in residential buildings. NM cable can be installed in walls, ceilings, and floors as long as it is protected from damage. It is not permitted to be used in wet or damp locations such as bathrooms, kitchens, or outdoor areas unless it is specifically listed for such use. Thirdly, the National Electrical Code, or NEC, specifies the installation requirements for non-metallic cable, or NM cable. NM cable must be supported and secured to the building structure using staples, cable ties, or other approved methods. The spacing between supports must not exceed 4.5 feet for horizontal runs and 12 inches for vertical runs. NM cable must be protected from physical damage where it passes through walls, floors, or ceilings. This can be achieved by using conduit sleeves or other protective measures. Fourthly, when installing non-metallic cable, or NM cable, it's important to avoid sharp bends or kinks that could damage the insulation. The minimum bending radius for NM cable is typically 5 times the diameter of the cable. When running NM cable through holes in studs or joists, the holes must be drilled in the center of the framing member to prevent the cable from being damaged by nails or screws. Fifthly, non-metallic cable, or NM cable, must be properly connected to outlets, switches, and light fixtures using approved wiring methods. The insulation must be stripped from the conductors carefully to avoid nicking or damaging the wires. Wire connectors, such as wire nuts or terminal screws, must be used to make secure connections. The connections must be made in accordance with the manufacturer's instructions and the NEC. Sixthly, grounding is a critical aspect of non-metallic cable, or NM cable, wiring. The ground wire in the NM cable must be connected to the grounding terminals of outlets, switches, and light fixtures. The grounding system provides a path for fault current to flow back to the source, tripping the circuit breaker or fuse and preventing electric shock. All metal enclosures, such as junction boxes and appliance housings, must be connected to the grounding system using grounding wires or grounding screws. Seventhly, when splicing non-metallic cable, or NM cable, the splices must be made inside approved junction boxes. The junction boxes must be accessible and securely mounted to the building structure. The splices must be made using approved wire connectors, such as wire nuts or terminal screws. The junction boxes must be properly covered to protect the splices from damage and prevent accidental contact. Eighthly, non-metallic cable or NM cable must be protected from physical damage and environmental factors. It must not be installed in locations where it is exposed to moisture, chemicals, or extreme temperatures. It must not be installed in locations where it is subject to physical abuse, such as in areas where it could be stepped on or run over. Ninthly, when working with non-metallic cable or NM cable, it's important to follow all safety precautions. Always disconnect the power supply to the circuit or area you'll be working on before starting any work. Use appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools to minimize the risk of electric shock or injury. Work in a well-lit and ventilated area to ensure good visibility and prevent the buildup of hazardous fumes. Tenthly, regular inspection and maintenance of non-metallic cable or NM cable wiring is essential for ensuring its safety and reliability. Inspect the cable for any signs of damage or deterioration. Check the connections at outlets, switches, and light fixtures to ensure that they are tight and secure. Replace any damaged or outdated components to prevent electrical hazards. By understanding the characteristics, applications, and installation requirements of non-metallic cable or NM cable, you can ensure that your residential electrical wiring is safe, reliable, and compliant with electrical codes.